Today we are going to study about vapor pressure of liquid solutions. And liquid solutions are the solutions. We know that in solution it is made up of solute and solvent. So the liquid solutions are the solutions where solute is solid or liquid or gas. Any one of the cases possible. And the solvent is always liquid. So the name it is liquid solutions. Now we will study one law called as Raoult's law in case of vapor pressure of liquid solutions. Before studying Raoult's law, we have to study about the vapor pressure of liquid solutions. And this liquid solutions are the liquid solutions where the solute is also liquid and solvent is also liquid. So both are liquid. Such solutions, they are called as liquid solutions. So let me consider liquid solution which is made up of two liquids, and I'll name one of the liquid as component 1 and another one as component 2. And both these liquids are volatile. Let me take these two liquids in a container which is having closed lid. Now let me make it to evaporate. And since both are volatile, component 1, that is liquid 1 and liquid 2, both will start to evaporate. And there will be equilibrium established between liquid and vapor phase. If that is the condition, let me take the vapor pressure of first component as P1 and mole fraction of first component as X1. And the vapor pressure of component 2, that is liquid 2, let it be P1, and the mole fraction of the liquid to be P2 and mole fraction be X2. So this is the condition. Now let us study Raoult's law. So this Raoult's law, it was given by Francis Mart Raoult, and it states that for a solution which is made up of volatile liquids, so already we know that in liquid solution both the liquids are volatile. In that case, the partial vapor pressure of each component of the solution, it is directly proportional to the mole fraction present in the solution. So if it is made up of two components, then according to Raoult's law, the partial pressure of each component, it is directly proportional to mole fraction of that component. In general, we can write it as P is directly proportional to X, where P is the partial vapor pressure of any component, either it may be component 1 or component 2. And X is nothing but the mole fraction of that component, maybe component 1 or 2. So we can write for Raoult's law the mathematical expression as P is directly proportional to X, and this proportionality is replaced by a constant, that is P naught, and this P naught, it's nothing but vapor pressure of pure component. So we can write P is equal to P naught into X. For component 1, we can write P1 is equal to P1 naught into X, and for component 2 we can write as P2 is equal to P2 naught into X. So for component 1 we can write P1 is equal to P1 naught into X. For component 2 we can write P2 is equal to P2 naught into X. So this is about Raoult's law. Just remember, the vapor pressure of any component, it is directly proportional to mole fraction of that component in case of Raoult's law, and it is applicable to liquid solutions, and both should be volatile. So that's about Raoult's law. Now let us apply Raoult's law to a liquid solution containing two liquids and both are volatile. Let me name it as component 1 and component 2. So for component 1, I can write Raoult's law as P1 is equal to P1 naught into X, and for component 2, I can name it as or write it as P2 is equal to P2 naught into, here it is X2, here it is X1. So let it be equation 1, this be equation 2. And according to Dalton's law of partial pressure, we can write as the total pressure of this solution represented as P total, that is the summation of partial pressure of all the components. Since there are two components here, it will be the total of partial pressure of two components, that is P1 plus P2. Let it be equation number 3. Now from 1 and 2, what we can conclude? From 1 and 2 we can write as, in the place of P1 you can put P1 naught into x1, and in the place of P2 you can put P2 naught into x2. So you will get P total is equal to P1 naught into x1 plus P2 naught into x2. And according to the concept of mole fraction, we will be knowing that the sum of the mole fraction of all the components, that will be equal to unity. Since there are two components here, I can write x1 plus x2 is equal to 1. So let it be equation number 4, and I'll name this equation as star. So from 4, what you can conclude? You can put, since x1 plus x2 is equal to 1, you can write x1 is equal to 1 minus x2. So let it be 5. Now put this 5 in equation number star. So put or substitute 5 in equation star. So you'll get P total is equal to, in the place of P1 naught you'll write as it is, in the place of x1 write 1 minus x2 plus P2 naught into x2. So we will simplify this one. So I'll just simplify. So I'll get P total is equal to P1 naught minus P1 naught into x2 plus P2 naught into x2. So now what I will do is, I will take x2 outside. So I'll get P1 naught minus, since I'll take x2 outside, I'll get here minus P1 naught plus P2 naught. So in turn I can write it as P2 naught minus P1 naught into this x2. So I got P total is equal to P1 naught minus x2 into P2 naught minus P1. So this equation tells that the total pressure of this solution, it is dependent on the mole fraction of the component 2. So either you can write component 1 or component 2. If you derive in the form of getting x1, the total pressure will be dependent on the mole fraction of x1. So the total pressure of this solution depends on mole fraction of any one of the components. So that is the conclusion. So let us see the graph of vapor pressure versus mole fraction of the component. So if you see the graph, you can understand that at this point there is only mole fraction of the component 1 and there is no fraction of component 2. That means this partial pressure is completely related to pure component 1. Similarly here the mole fraction of x1 is 0 and x2 is equal to 1. So this suggests that the partial pressure of this partial pressure is nothing but the partial pressure of pure component 2, since x1 is 0. And we can also see that the total vapor pressure, that is the sum of partial vapor pressure of component 1 and component 2, that increases with the increase in mole fraction of x2. From here to here x2 is increasing. So as x2 component is increasing, the partial total vapor pressure also increases. And it should decrease with the increase in mole fraction of component 1, because from here to here the mole fraction of component 1 is going on increasing. So the total vapor pressure should decrease with the increase in mole fraction of component 1. So we'll get two different lines and we will see the intersecting point, and finally we can find out the total vapor pressure. So the conclusion is that the total vapor pressure varies with the mole fraction of any one of the component, as we have derived the equation earlier. The total vapor pressure will be varying with the mole fraction of any one of the component, and the total vapor pressure increases with the mole fraction of the component 2. That is the conclusion. So this is about application of Raoult's law to the liquid solution which is containing two components,